Hey everyone, it's that guy who won't stop talking about machine learning. Today we're going to do a little bit of coding, so I hope you're ready for that. So I have this link here that I sent to you and and they're on the slides, the full slides. So this is a Google Colab notebook. So what you're going to do when you see this is you are going to open it with Google Colab. You may need to add it from here. So you're going to open it, and it should look like this. And you're going to need to copy it. I'm not going to copy it because this is mine, but you can make a copy of it so that you can edit it and play around with it a little bit. Otherwise, we can just run it. So we're going to go through here and run each of these blocks of code. This is how notebooks are set up. It allows you to just run code in place and change these. And what's happening is that a Google server is actually running all of your code. It's a nice little thing to have because it doesn't rely on you having a very good computer, and it's used a lot in machine learning. All right. So first, we have to install our libraries. You can actually have to pip install them because we essentially are creating a little virtual machine over on a Google server. All right, so we install them. We have to import the dependencies. This is Pytorch right there, the import torch. These are our data sets. These are our transforms. We'll get to them each. All right, so now we get here, which is defining our hyperparameters. So this is the first sort of important thing that we need to do. So first, we have to define our input size, which we have as 784, like we do in our example. If you recall, it was MNIST, which is 28 by 28 images of grayscale values. We're also going to define here a hidden size of 500, which is fairly large and was a lot bigger than the size we were talking about before. And of course, we have our number of classes being 10, which is the number of classes in MNIST. The number of epochs here is equal to the number of times we're going to go through the entire data set. So MNIST consists of 60,000 labeled images. And when we say that we are going through 20 epochs, that means we are going through those 60,000 images 20 times. So we're going to train through them 20 times. It is actually 50,000 for the training set, so we're only going to go through 50,000 20 times, but still, it's very high. Batch size here we haven't talked about, and we will probably be talking about in a later video. Batch size essentially is how many images we are taking in at the same time. One nice property of our neural networks is that we can take multiple images at the same time and get a generalized gradient out of them, and so we like that. And we will generally want this to be fairly high because it will increase the speed of our training and will also sometimes give us more general results. LR right here is our learning rate, which is the size of the steps that we're taking when we're updating our parameters. So you can see here it's fairly small, it's 0.001, and in general it is actually that small. We will see that our learning rate will be fairly small most of the time. So this is not out of the ordinary. So we just define those, all well and good, and here we get to actually import our data. So here we're using the Torch Vision dataset. So we have our torchvision.datasets, we are importing it as dsets. So we're using that to import our MNIST dataset both as a training set and as a testing set. So I'll leave it up to you to try to decide why we need both a training set and a testing set, like what would happen if we just trained on all of it. We'll talk about that more later as well, but you can just sort of think on it. So here we will use this dsets to import both of these. It will automatically download them to your computer, and it will allow us to format it so that we can just iterate over them to get new pieces of data. And in fact, that's what we're doing right here, is making them data loaders. So the data loaders will allow us to just iterate over these generators, these train generator and test generator, allow us to just iterate over them and get new pieces of data. So we need to have, this format is very nice. It's a lot easier than actually importing the data yourself and formatting and all that, and it will just import it in a uniform fashion. So we like to have those for any normal data set, for any data set that is included in this package. So there's only so many pre-programmed in, but you basically would just need to change this name really to change which data set you're importing. So it's very nice and very easy. Now we get to actually define our model. So this is our network right here. There are two important parts about defining our network with Pytorch. One, we have to initialize all of our different units that we're going to be using. So we're going to have an FC1, which is fully connected 1 layer. We're going to have fully connected 2 and fully connected 3. So there's going to be 3 different fully connected layers in our network. So we're actually getting a slightly bigger network than the one that we described in lecture. We're just adding an extra hidden layer. We also are defining ReLU. So ReLU is something we're going to talk about more later. It's what's called a nonlinearity. And for now, you don't really need to know about it. Just know that we need to put one in between each of our fully connected layers, and we'll talk about more why that is later. All right, so we define each of those, and then we need to define our forward pass. So our forward pass defines what our network is calculating. So we will go through our fully connected layer once, then we will go through our ReLU, then a fully connected layer 2, and then we'll go all the way until we return output. So this will just do our matrix multiplication and our ReLUs, like we described before, and it will just give us the output. The reason we need to define it like this, and the reason we have to use these linears and these nonlinearities, is so that Pytorch in the background can keep track of the parameters of each of these, and can actually keep track of the values we get as we go along this network, so that it can automatically do the backpropagation for us and get the gradient of the entire input. So it is very good. It's a very, very convenient thing that Pytorch does for us. So thank your stars is out while you're learning machine learning. You need to run this to initialize it. Very good. And then we're going to actually create the network. So net right here is going to initialize a network module, and it will take the input, hidden, and num class size that we had above. Right? So we will make that. Very good. This right here is Cuda. So Cuda is NVIDIA's onboard graphics card like units that will actually help speed up your machine learning training. Most NVIDIA graphics cards do have them, and if you convert it into a Cuda, you need to have the Cuda like installed on your computer. You need to actually install it if you want to run it. But if you use Cuda, it will in general speed up your train time quite a bit. So it is a good thing to do, and all you need to do is change it to net.cuda, and it will work like that. So we just run that. Very good. We've created our network now. And now we have to define our loss function and our optimizer. So right here we are using, right now we're using cross entropy loss as our loss function. This is one that's specific to doing this sort of classification task. So what it really is going to do is going to compare like the label as a vector, and it's going to compare them like we were talking about before and can optimize them. Here we are choosing an optimizer. We can use Atom here is a very good one that is good to know, but we could just as easily change it to SGD. You can see it is just .sgd, and that's totally fine. Let's use that one for this example. So we can just run this, and it will define both our loss function and our optimizer, and then we get to the good stuff. This right here is our actual training cycle. You can see it's actually very small. So we're just going to iterate over the epochs, so we're going to do it epoch number of times, and then we're going to enumerate over our train generator. So like I said, we can just enumerate over it, and it will give us images and labels as a tuple. So we're going to take those, and we're going to get our image, right? So we're going to actually, what this is doing right here, when it says images.view -1 2828, is it is restructuring, because we have right now a 28 by 28 image, but the way that we've structured our neural network is that we only take in a one-dimensional input. We only want a one-dimensional input. And so what we do is we use view -1 2828, converts it into a one-dimensional vector. It actually is removing a dimension when you have the -1 right there. That's what that means. And we are converting it to a 28 by 28 long thing. And we add the .cuda to convert it to Cuda. Right, so we have to define those as variables because we are going to be changing them. It's a weird property of this. I think we could actually get away with not doing that too, but in here we do. So now what we want to do, our loop of training, is we set the optimizer to 0. We're going to have to do this after every iteration, and you'll see why in a second. Then we're going to get our actual outputs. So we're just going to feed in the network that we defined earlier. We're going to give it the images that came in, the image that we are currently looking at, or images since it's a batch. And what this does is it just runs the forward pass. So it will just go through forward, and it will go through all of this, right? Very easily, and it'll just give you what the output is. Then we just put it through the loss function. We give the outputs and the labels, and it will tell us what our loss is. And when we do loss.backward, it will calculate the gradient of our entire network, which is very nice. This one line does all of the backpropagation for you. It's very good. So now, after we've done that, we have in our like neural network modules here, we have what the gradient is, and then all we need to do is optimizer.step, and what that will do is it will do our optimization step. It will move each of the parameters its desired amount based off of whatever learning rule we have in place. So in this case, SGD. So it will just take a step. And then the reason that we need to zero out now is we loop back around. When we zero out, it takes away, like we've built up now what the gradient is, and it will keep it as a value on our modules, and we need to zero them so that next time we don't like additively keep adding our gradients together. So that's why we zero them. And this right here is just a little printout so that we can see our progress as we go along. So now we can just run it, and you can see it'll start running. As it goes, it'll go through the steps, and you can see the loss should incrementally go down bit by bit as we train. Again, stochastic gradient descent is fairly slow, but you will see a significant improvement. MNIST is a fairly easy task, so at the end we expect to see pretty good results from it. Again, you can see it's already going down from like 2.3 to 1.5. Now, something to note about this is that our loss going down is not exactly the same as our performance being better, necessarily. By the definition of our loss function, it is better, so it is doing better in terms of our loss function, but that does not mean that our network will have higher accuracy. This does sort of loop back to why we have a train set and a test set. You, again, can try to figure that out on your own. I expect you should actually be able to sort of figure out why. It's an interesting part of ML. It's an important part too, where we have that. But while this trains, let's talk about what you might want to do if you want to change this network. And I do recommend, when you're looking at this code, to try changing something and just play around with it. Like, you might break it, that's fine, but you can try stuff. One of the easiest things for you to do is you can just change the hyperparameters. For example, say I wanted to have more parameters. I could just update the hidden size to 600, and that would mean that now, instead of having 500 on each of those, I have 600, and it's very good. I could change the number of epochs. Maybe I am training too much. Maybe I'm training too little. I could change the batch size. I could change the learning rate. All of these things. You can't really change the input or the num class size because we have a specific data set. But you could, in fact, try changing the data set. A common one is Safar. I think Safar 10 is how it's labeled. I think it's probably all caps, actually. Probably Safar 10, and that is 32 by 32 by 3 images. And it's a very nice data set for you to play with too. It's slightly harder than MNIST, so it gives you some leeway to try to find a better score. You could also try changing the structure of this. Maybe 3 layers isn't enough. Maybe you need 5 layers. You could just add another, like if I wanted to, I could just do like self dot or out equals self dot fc2 out, because this goes from one size to its same size, and I could just add another ReLU, and all of a sudden we have a slightly different network. So we can do stuff like that as much as we want. We can change which optimizer we use, we can change which loss function, and you can see how all those different things affect it. There's a lot of moving parts here, and it's pretty hard to tell immediately how they would actually change your network. So it's good to play around with them and see. So let's see how it's going. So it looks like at the end here, we actually saw that our scores started going up again, and that is an indicator that we are overtraining. It still is like decent. I guess it has gone down on average, but there are some spikes here. So it has trained fairly well, and now we expect that if our loss is this low, we probably have pretty good accuracy. This little bit of code right here is just to check the accuracy. You can look through it yourself. It's very straightforward code. And let's see how our model fared. 89%. Well, I put it on you guys. See if you can do any better. I fully expect that you could make some simple changes and you would get much better performance out of this network. All right. Well, hope you have a good day. See you around.